Look at Saturn through any telescope and you see something that feels eternal. A planet wearing a halo of ice so perfect it looks designed, unchanging, permanent. For 400 years, every astronomer who pointed a lens at it saw the same rings. They look like furniture. They look like they have always been there and always will. But they have not, and they will not. Down at Saturn's cloud tops, instruments have caught the rings in the act of vanishing water and dust streaming out of them, pouring into the planet at thousands of kilograms every second. Saturn is swallowing its own crown. The most famous structure in the solar system is leaking into the world it orbits, and we may be watching the final act. Before we dive in, if stories like this are why you're here, a quick like and subscribe genuinely helps the channel more than you'd think, and it's free. That's it. Now, settle in and get yourself comfortable. Let's begin. Begin not at the rings, but in the sky beneath them. High above Saturn's cloud tops, in the thin electrified shell of gas we call the ionosphere, something was glowing wrong. Astronomers had pointed some of the most sensitive infrared instruments on Earth at the planet, expecting a particular kind of light, the faint, steady shine of a molecule called triatomic hydrogen, written as H3+, a hydrogen ion built from 3 protons and 2 electrons. When sunlight energizes that ion, it glows in the infrared. Every gas giant should wear this glow like a smooth, even blanket across its upper atmosphere. Jupiter does exactly that. Its equatorial regions shine with a calm, uniform light, the way a well-lit ceiling glows evenly from edge to edge. Saturn refused to behave. Instead of a smooth blanket of infrared light, the telescope saw stripes. Bands of brightness broken by bands of darkness, alternating across the planet's upper atmosphere like the marks left by fingers dragged through wet paint. In some latitudes, the glow was strong. In others, it simply collapsed, dimmed, went quiet. And when researchers lined up those dark stripes against the structure of the rings far overhead, the pattern snapped into focus in a way that was impossible to ignore. The dark, quenched zones sat directly beneath the densest, most water-rich sections of the rings. The bright zones lined up with the gaps. The rings were printing their own shadow onto the planet's chemistry. This was the first hard piece of the puzzle, and it came not from a spacecraft but from the ground. Much of the key work led by a team using the Keck telescope perched on Mauna Kea in Hawaii. They tracked the H3+ emission with care, mapped where it thrived and where it died, and reached a startling interpretation. Something was reaching down out of the rings, falling into the atmosphere, and switching the glow off. The leading explanation, and it remains the leading explanation today, is that electrically charged particles of ring water were sliding down into Saturn and neutralizing the very ions that produce the infrared shine. Where the water fell, the light went out. The dark bands were not shadows of sunlight at all. They were chemical bruises, places where infalling ring material was actively rewriting the atmosphere, and the bruises were enormous. These quenched zones were measured to cover somewhere between 30 and 43% of the surface of Saturn's upper atmosphere, spread across the mid-latitudes, roughly from 25 to 55 degrees north and south of the equator. That is not a trickle leaving a faint mark in one small spot. That is a planet-wide effect, painting nearly half of Saturn's upper atmosphere with the fingerprint of its own rings. And it was a far larger area than anyone had expected from the older, blurrier hints captured decades earlier. Because there were older hints. This is where the trail of evidence actually starts, and it is worth following backward for a moment, because it shows how long Saturn had been quietly confessing. In 1981, as the Voyager 2 spacecraft swept past Saturn on its grand tour of the outer solar system, it photographed the planet's hazy upper atmosphere and caught something subtle, a trio of narrow dark bands encircling Saturn at northern mid-latitudes. At the time, nobody could say with confidence what they were. They were just peculiar. Saturn also showed strange, unexplained variations in its electrically charged upper atmosphere, and odd density patterns threaded through the rings themselves. 3 separate oddities, seemingly unrelated, filed away as curiosities. Then, in 1986, a scientist named Jack Connolly did something that turned scattered curiosities into a theory. He noticed that the position of those narrow dark bands matched the geometry of Saturn's gigantic magnetic field. He proposed that electrically charged ice particles from the rings were flowing down invisible magnetic field lines, like beads sliding along a wire, and dumping their water into Saturn's upper atmosphere exactly where those field lines plunged into the planet. The water washed away the high stratospheric haze, and the cleared, darkened lanes were what Voyager had photographed as narrow bands. It was an elegant idea. It was also, for years, just an idea, a leading hypothesis waiting for someone to fly close enough to test it. That someone was Cassini, and the way Cassini tested it was by dying. By 2017, the Cassini spacecraft had spent more than a decade orbiting Saturn, mapping its moons, threading its ringlets, watching its storms. It was running low on fuel. Mission planners faced a choice about how to end it, and they chose something audacious. Rather than letting the spacecraft drift uncontrolled and risk one day crashing into a moon like Enceladus, which might harbour conditions for life, they decided to send Cassini somewhere no probe had ever gone directly into the narrow gap between the planet's cloud tops and the inner edge of the rings. Not once, but 22 times. A series of dives through a slot only a couple of thousand kilometers wide, each pass bringing the spacecraft screaming through the empty-looking space between Saturn and its bangles before swinging back out. They called it the grand finale. It was, in effect, a controlled fall toward the planet, with the final plunge scheduled to vaporize the spacecraft in Saturn's atmosphere in September of that year. Here is the detail that tells you how much material the scientists already suspected was there. As Cassini made these dives, it was traveling at roughly 77,000 miles per hour, vastly faster than any rifle bullet, fast enough to cross the United States in a couple of minutes. At that speed, even a single grain of dust hits like a bullet. So the team deliberately turned the spacecraft, pointed its large radio dish forward, and used the dish as a shield, as an umbrella. They expected to fly through rain, and they wanted something to hide behind. What happened next reshaped the entire question. One of Cassini's instruments was the ion and neutral mass spectrometer, a device designed to sniff gases to identify atoms and molecules by their mass. It was never built to catch solid particles. But as the spacecraft tore through the gap, ring particles slammed into the instrument so hard that they vaporized on contact, flashing instantly from solid grains into gas, the way an insect bursts against a windshield at highway speed. And in that flash of vapor, the spectrometer could read them. By accident of physics, an instrument meant for gas became a tool for tasting the falling rings. What it tasted was a flood. The team had braced for a trickle. The textbook version of ring rain, the version everyone carried in their heads, was a thin drizzle of mostly hydrogen and a little water seeping down from the innermost ring. Modest, tidy, nothing fancy. Instead, the instrument registered material pouring into Saturn at something on the order of 10,000 kilograms every single second. 10 metric tons of ring, gone into the planet, every tick of the clock. The lead scientist on that instrument, Hunter Waite, summed it up in a line that became the headline of the whole result. Ring rain is more like a ring downpour. And it was not just water. This is the part that genuinely unsettled people. The rings are made of ice, almost nothing but frozen water, a vast orbiting field of it, with barely a trace of anything else. So the rain should have been overwhelmingly water. It was not. The spectrometer detected molecular hydrogen, yes, and water, but also carbon monoxide, methane, nitrogen, and a confusing zoo of complex organic molecules, even compounds related to butane and propane, the kind of carbon-rich chemistry nobody had ordered. Material that should have been a clean glass of meltwater came back tasting like an industrial cocktail. Stranger still, there was less water ice in the rain than the composition of the rings predicted. If the rings are almost entirely ice, why was the downpour relatively poor in it? One proposed explanation, and it is a hypothesis rather than a settled fact, points to a previously undetected belt of radiation tucked in close to the planet, threaded through the innermost ring. The idea is that this radiation strips water away from the icy grains as they fall, so that what survives the journey down to where Cassini sampled it is enriched in the tougher, radiation-resistant leftovers, the silicates and organics, while much of the water has already been pulled off elsewhere. In other words, the rain may be sorted on its way down, with different materials peeling off at different stages. It is a clue not just about how much is falling, but about how the falling itself works. Now, here is where an honest account has to slow down and resist the temptation of a single clean number, because the truth is messier and more interesting. 3 different research teams analysed material falling into Saturn, and they came back with estimates that disagreed wildly, not by a little, but by factors of thousands. On the low end, one analysis suggested that only around 10 pounds of nanograins per second were drifting down from the innermost ring, a genuinely gentle drizzle measured in a few kilograms. On the high end, another estimate reached an astonishing figure on the order of 99,000 pounds of water, ice, organics and silicates falling every second, roughly 45,000 kilograms, from a few kilograms to tens of thousands of kilograms per second, all from the same planet, all from the same mission. That spread is not a failure. It is a signpost. The teams were measuring different materials, with different instruments, at different locations around the planet. One was counting tiny charged grains seeping from one ring at mid-latitudes. Another was catching the full chemical torrent crashing into the equator. They were not contradicting each other so much as describing different parts of the same elephant in the dark. And the very fact that the numbers refuse to converge is itself a discovery. Whatever is happening, it is not one simple process with one simple rate. It is several pathways at once, varying from place to place, and possibly varying over time. That last possibility, varying over time, matters enormously, and the Cassini data hinted at it directly. The instrument measured differences in the rainfall from one orbit to the next, just days apart. That could mean certain stretches of the innermost ring are physically different and produce more rain than others. Or it could mean the whole downpour fluctuates, surging and easing on timescales we have barely begun to sample. We caught Saturn in the act over a window of weeks. We do not yet know whether those weeks were typical, or whether we happened to arrive during a storm. There is a reason that window might not have been typical, and it has to do with the seasons. Yes, the seasons. On a planet nearly 10 times farther from the Sun than we are, Saturn is tilted on its axis by roughly 27 degrees, almost the same tilt that gives Earth its summers and winters. And because Saturn takes about 29.5 years to circle the Sun, each of its seasons lasts something like 7 years. As the planet swings through that long orbit, the rings are presented to sunlight at constantly changing angles, sometimes tipped wide open toward the Sun, sometimes turned nearly edge-on. This matters enormously for ring rain, because sunlight is one of the engines that charges the ring grains in the first place. Ultraviolet light from the Sun is part of what gives a grain the electric charge it needs before the magnetic field can grab it. So as the lighting on the rings changes across Saturn's seasons, the rate at which grains get charged should change too, and with it, the rate of the rain. The scientists who measured the downpour were explicit that they wanted to come back and watch how the ring rain shifts with the seasons, precisely because they suspected it was not a constant. We did not just sample a narrow window in time, we sampled it during one particular season, under one particular angle of light, and the planet may rain harder or softer at other points in its long year. That seasonal rhythm shows up in another ghostly feature of the rings, one that has haunted astronomers for decades and ties directly into the charging story. They are called spokes, faint, dark, radial smudges that appear across the rings like the spokes of a bicycle wheel, sweeping around with the rings before fading after only 2 or 3 rotations. Voyager 1 first photographed them in 1980. Cassini saw them, and the Hubble Space Telescope, watching Saturn year after year, has caught them coming and going on a seasonal schedule, growing more frequent and darker as the planet approaches the moments in its orbit when the rings are tilted least relative to the Sun. The leading explanation is that the spokes are dust, tiny ring particles electrostatically levitated, lifted clear off the ring plane and made to hover above it by electric charge. After several decades, no theory perfectly predicts them, and they remain a genuine open puzzle. But for our purposes, their lesson is unmistakable. If electric charge can pluck dust grains straight up off the rings and hold them suspended in defiance of gravity, then charge is not a minor bookkeeping detail in this system. It is a force strong enough to move ring material around at will. The spokes are the visible, photographable proof that the rings are electrically alive, and that same electrical life is what feeds the rain falling into the planet below. And then there was the equator, the place where Cassini found something nobody had predicted at all. Two more instruments tell this part. The first, the cosmic dust analyzer, was built to catch and characterize tiny solid grains. As Cassini crossed the gap between the innermost ring and the outer atmosphere, the analyzer found that this supposedly empty slot was not empty. It was filled with a fairly steady population of grains of water ice and silicate, each only a few tens of nanometers across, particles so small that thousands could sit side by side across the width of a human hair. This was a constant, drifting haze of falling ring material, threading the gap that Cassini was diving through. The second instrument went smaller still. The magnetospheric imaging instrument, designed to detect energetic neutral atoms and charged particles, picked up even tinier grains, comparable in size to particles of smoke, hanging at altitudes of roughly 1,700 to 3,000 kilometers above Saturn's equator. And the principal investigator on that instrument said plainly that there had been no expectation of dust sitting right at the equator. The mid-latitude bands, the ones tied to the magnetic field, those had been predicted for decades. But a population of fine grains concentrated directly over the equator, falling more or less straight down, was a genuine surprise. It meant the planet was being fed by at least two different delivery systems at once, one steered by magnetism into the mid-latitudes, and another dropping material almost vertically onto the equator. Step back and hold all of this together, because the weight of it is the whole point of where we are in the story. We did not infer that ring material falls into Saturn from a single ambiguous clue. We have, layered on top of one another, a stack of independent detections, gathered by different methods that all point the same way. From the ground, telescopes watch the infrared glow of Saturn's atmosphere collapse in stripes that match the rings overhead. From orbit decades earlier, Voyager caught narrow dark bands that a magnetic field model later explained as lanes of infalling ring water. And then, in its final weeks, Cassini flew straight through the falling material and tasted it directly, a mass spectrometer reading the chemistry, a dust analyzer counting the grains, an imaging instrument finding an unexpected haze over the equator. Ground-based observation, decades-old imagery, and direct in-place sampling, all converging. It is worth pausing here on just how much those final 22 dives delivered, because the ring rain was only one prize among many, and the others sharpened the picture of a planet and its rings that are far more entangled than anyone had pictured. The grand finale was, in a sense, the most productive few weeks of the entire 13-year mission, precisely because Cassini went somewhere it had spent a decade carefully avoiding. Consider the most basic question you could ask about a planet. How long is its day? For Earth, the answer is obvious: you watch the sun, or a landmark, come back around. But Saturn is a featureless ball of gas with no solid surface to track, and worse, its magnetic field is so nearly aligned with its spin axis that the usual trick astronomers use on other giant planets simply fails. On Jupiter, the magnetic pole is tilted, so it swings around as the planet turns and sends out a regular radio pulse you can time like a lighthouse. Saturn, with its strangely upright field, sends no such clean signal. For decades, the length of a Saturn day was genuinely unknown, with estimates scattered across a range of many minutes, an embarrassing gap in our knowledge of one of the most studied planets in the sky. And the thing that finally closed that gap was the rings. The breakthrough came from treating the rings as a seismograph. Saturn's interior, it turns out, vibrates, oscillating at frequencies set by its internal structure. The way a struck bell rings at notes determined by its shape, those vibrations cause tiny rhythmic variations in Saturn's gravitational field, and the ring particles orbiting in that field cannot help but feel them. At specific locations in the rings, the oscillations catch the particles at just the right moment in their orbits and build up waves, spiral patterns rippling through the ice, driven from inside the planet. By reading those wave patterns in the rings, a researcher named Christopher Mankiewicz was able to work backward through the gravity field into the planet's interior, and out came the answer: a Saturn day is about 10 hours, 33 minutes, and 38 seconds long. The rings held the answer, Let that sink in as a statement about how connected this system is. We measured the spin of the planet's hidden interior by watching ripples in the ice orbiting thousands of kilometers above it. The rings are not a separate object hanging in the sky near Saturn. They are a recording instrument wired into the planet's deepest physics, and we only learned to read them because Cassini flew close enough to see the ripples in detail. Then, there was the matter of the gap itself, the slot between the innermost ring and the cloud tops that Cassini was diving through. Before the grand finale, no one knew with confidence how wide that gap really was, or what was in it. The spacecraft found the rings sitting startlingly close to the planet, and the gap, as we have already seen, was not the clean empty space the mission planners had braced for, but the surprise cut both ways. Cassini also mapped the structure of Saturn's ionosphere as it passed through, and found it was not a single uniform shell but layered a lower region near the equator, beneath the rings, holding larger neutral and charged molecules, and above it a thinner, sparser layer of tiny charged particles. The very architecture of Saturn's upper atmosphere bore the imprint of the rings raining down through it, sorted into layers by the flood of material from above. Even the planet's electrical envelope had been reshaped by its rings, and woven through all of this was the gravity and magnetic mapping itself, the core scientific purpose of those final orbits. By flying so close and falling freely, Cassini let Saturn's gravity and magnetism write themselves directly into the spacecraft's motion, allowing scientists to probe the planet's interior structure and weigh its rings with a precision no distant flyby could ever achieve. A measurement we will return to when we ask how old the rings actually are. The point for now is simply this: the falling ring material was not an isolated curiosity. It arrived as one finding among a whole interlocking set, every one of them pointing at the same conclusion from a different angle, that Saturn and its rings are not a planet and its decoration, but a single, deeply coupled system, and that we had been studying only its surface until the moment a dying spacecraft finally dove inside. When evidence from completely different instruments and completely different eras lines up like that, you are no longer looking at a guess. You are looking at a confirmed fact. Material is leaving the rings and entering the planet, right now, continuously, through more than one door. But confirming that it happens immediately raises a puzzle that the scientists themselves could not ignore, and it is the puzzle that will drive everything that follows. Run the arithmetic at the high end of those falling rates, and you get something absurd. If material truly poured out of the rings at tens of thousands of kilograms per second and never stopped, and if nothing refilled them, the rings would empty themselves not over the lifetime of the solar system, not over billions of years, but in a geological blink by some back-of-the-envelope estimates, in as little as tens of thousands of years. That is shorter than the span since the first cave paintings were made on Earth. And that creates an obvious contradiction. The rings are clearly still here. We can see them from our backyards. So if they were draining that fast and had been for ages, they would already be gone. There are only a few ways out of that contradiction, and each one points toward a deeper question. Maybe we caught Saturn during an unusually heavy downpour, a temporary surge, perhaps kicked off by a recent collision with a comet or a chunk of icy debris that briefly loaded the system with extra material. In that case, the high rate is real but rare, and the long-term average is gentler. Maybe the innermost ring is being constantly refilled from the ring just outside it, fed a fresh supply from a deeper reservoir, so that what looks like rapid loss in one place is partly a handoff from another. Or maybe the rings are simply more dynamic than they look, not a frozen, finished sculpture, but a churning, turning over structure that loses material and reshuffles it on timescales we are only starting to measure. As one researcher put it, the real story the data tells is not about a fixed object quietly evaporating. It is about churn, a system in motion, surviving precisely because it never sits still. Notice what every one of those explanations has in common. All of them concede the central, uncomfortable truth that the rest of this story is built on. The rings are not inert. They are not a permanent ornament bolted to the planet. They are an active structure, exchanging mass with the world below them, leaking and possibly refilling. And the only real debate is about the rate and the balance, not about whether it is happening. It is happening. Saturn is eating, whatever the size of the meal. And that hands us the question that the falling material cannot answer on its own. The question that turns this from a list of detections into a story about a machine. We have established what is falling, and roughly how much, and where it lands. We have water and silicates, and a strange broth of organics. We have charged grains threading down magnetic field lines into the mid-latitudes, and an unexpected haze of fine particles dropping onto the equator. We have a planet wearing the chemical bruises of its own rings across nearly half its upper atmosphere, but we have not yet explained the thing that should be physically baffling about all of it, because a ring particle is not supposed to fall. Out in the ring plane, every grain of ice is in orbit, circling Saturn at tremendous speed, held in a near-perfect balance between the planet's gravity pulling it inward and its own orbital motion carrying it forward. That balance is stable. It is the same balance that keeps a moon in its place, or a spacecraft in a parking orbit for millions of years. Left alone, an icy grain in Saturn's rings should just keep going around and around and around, never falling, never climbing, indefinitely. So what breaks the balance? What reaches into a stable orbit, singles out a particle, and drags it down out of the sky and into the planet? What turns a permanent-looking ring of ice into a downpour? That is not a question about chemistry. It is a question about forces, about gravity and magnetism, an electric charge working together on grains smaller than smoke in a place where a planet and its rings turn out to be wired into each other as a single connected machine. The detections told us the rain is real. To understand why it falls, we have to take that machine apart and see how Saturn reaches up and pulls its own crown down into itself. That mechanism is where we go next. Start with the thing that should be impossible. A grain of ice in Saturn's rings is in one of the most stable situations in all of physics. It orbits. That single word carries more permanence than almost anything else in nature. To orbit is to fall forever without ever landing, to be pulled toward a planet by gravity while moving sideways so fast that you keep missing it. The grain races along its circular path at many kilometers per second. Gravity bends that path into a closed loop, and the two effects lock into a balance so precise and so durable that it can hold for hundreds of millions of years without anyone tending it. This is why moons stay up. This is why a spacecraft, once parked in the right orbit, needs no engine to keep circling. Orbit is the closest thing the universe offers to a structure that maintains itself for free. So when we say material is falling out of Saturn's rings and into the planet, we are describing something that on its face should not happen. Nothing in a stable orbit simply decides to come down. To make a ring particle fall, something has to reach into that perfect balance and break it. Something has to steal energy from the grain, or push it, or grab it, and drag it off its track. And the central revelation of this whole story, the thing Cassini and decades of patient work uncovered, is that Saturn has not one but several different ways of doing exactly that. The planet is not passively holding its rings. It is actively reaching up and pulling them down through more than one mechanism at once. To see how, we first need to define the phrase that gets thrown around so loosely, ring rain. It sounds poetic, and it is, but poetry hides the machinery. Let us be precise about what it actually means, because precision here is the difference between understanding and hand-waving. Ring rain, in its original and narrowest sense, refers to a very specific process. Electrically charged particles of ring water being guided down into Saturn's atmosphere along the planet's magnetic field lines. Not gravity simply sucking ice down, not the rings vaguely dissolving. A particular, traceable pathway in which a grain becomes charged, and once charged, stops behaving like a free body in orbit and starts behaving like a bead threaded onto a magnetic wire, sliding down that wire into the planet at specific latitudes. That is the real definition, and everything else we have detected falling into Saturn is either a variation on it or a genuinely separate process wearing the same name. Holding that distinction clearly in mind is what keeps us honest, because, as we will see, not everything that rains is ring rain in the strict sense. So let us build the mechanism from the grain up. Begin with a single mote of ice sitting in the innermost reaches of the rings, quietly orbiting. As long as that grain is electrically neutral, the magnetic field of Saturn means nothing to it. Magnetism only grips things that carry an electric charge. A neutral particle sails straight through a magnetic field as if it were not there, feeling only gravity and its own motion. So the first step in pulling a grain out of the sky is to give it a charge. And Saturn has charging agents in abundance. The most important is sunlight. Ultraviolet photons from the sun strike the icy grains and knock electrons loose, a process that leaves the grain electrically charged. Plasma, the soup of charged particles filling the space around Saturn, does similar work, depositing or stripping charge as grains move through it. In the harsh, irradiated environment near the planet, a small grain does not stay neutral for long. It picks up a charge, and the instant it does, its situation changes completely. It is no longer just a tiny rock obeying gravity. It is now a charged object sitting inside one of the strongest magnetic fields of any planet in the solar system, and the magnetic field now has a handle on it. Here is where the balance breaks. For a large particle, gaining a little charge barely matters. Gravity still dominates because the particle is heavy and the electromagnetic force is comparatively weak. But for a very small grain, the arithmetic flips. As particles get smaller, their mass drops far faster than their surface area. So, the forces that act on the surface, including the electromagnetic grip of the magnetic field, become large relative to the gravity acting on the tiny mass. For grains in a certain narrow size range, the magnetic force becomes comparable to, and can override, the simple gravitational orbit. The grain stops being primarily a thing in orbit and becomes primarily a thing controlled by the magnetic field. That is the tipping point. That is the moment a permanent-looking ring particle is condemned to fall, and once the field has it, the path is determined. Saturn's magnetic field lines arc out of the planet, sweep through space, and plunge back into the atmosphere at specific latitudes in each hemisphere. A charged grain caught on a field line that threads the ring plane will be guided along that arc, sliding down toward the planet and entering the atmosphere precisely where that field line dives in. This is why the infalling water does not splash down evenly across Saturn. It arrives in bands, at particular latitudes, the same mid-latitude lanes, around the mid-40s of degrees north and south, where the dark stripes appeared in the infrared glow. The grains are not falling randomly, they are being routed, sorted by the geometry of the magnetic field into narrow zones of impact. The dark bands Voyager photographed in 1981, the quenched stripes in the H3+ glow seen from the ground, the latitudes where the ionosphere goes quiet, all of them are the footprints of grains arriving at the bottom of their magnetic slides. Now, Saturn's magnetic field has a peculiarity that makes it unusually good at this job, and it is worth pausing on because it is genuinely strange. On nearly every other planet with a magnetic field, the magnetic axis is tilted relative to the spin axis. Earth's magnetic poles wander away from its geographic poles. Jupiter's field is tilted by about 10 degrees. This tilt is, in fact, part of how planets are thought to generate magnetic fields in the first place. But Cassini measured Saturn's field during the grand finale and found it almost perfectly aligned with the planet's spin axis tilted by a fraction of a degree, far less than any other planet studied. This near-perfect alignment is itself an unsolved puzzle, because the leading theories of how planets make magnetic fields struggle to explain how Saturn maintains one without a meaningful tilt. But for our story, the consequence is what matters. A clean, axially symmetric field is an efficient, orderly delivery system. It threads the rings and the atmosphere together in a smooth, predictable geometry, channeling charged grains down into tidy latitude bands rather than scattering them. Saturn is, in a sense, unusually well engineered to drain its own rings. That is the strict mechanism of ring-rain charge: capture, slide, arrive. And for a long time, that was the whole picture. A slow, magnetically guided seep of water into the mid-latitudes, real but gentle. If that were all Saturn did, the rings might last a comfortably long time. But Cassini's death dives revealed that the mid-latitude seep is only one door, and possibly not even the main one. Recall what the spacecraft found waiting in the gap between the innermost ring and the cloud tops. The slot everyone had assumed was nearly empty. It was full of falling material, and crucially, much of it was falling onto the equator, not the mid-latitudes. The cosmic dust analyzer found a steady population of ice and silicate grains, tens of nanometers across, drifting through the gap, The magnetospheric imaging instrument found even finer, smoke-sized grains hanging over the equator, and the mass spectrometer registered that torrent of 10,000 kilograms per second of mixed chemistry slamming into the equatorial region. This was not the orderly, magnetically routed drizzle of the mid-latitude bands. This was a heavy, broad influx coming down near vertically onto Saturn's waste. That distinction, equatorial versus mid-latitude, is one of the most important and most underappreciated points in the entire subject. So let us make it sharp. The two pathways are physically different. The mid-latitude bands are the work of charged grains following magnetic field lines. This is ring rain in the classic sense, electromagnetic, latitude-specific, sorted by the field. The equatorial influx appears to be something else. Material falling more directly under gravity, dragged down once its orbit has decayed enough to bring it into the fringes of the atmosphere, raining onto the equator, because that is simply where the ring plane meets the planet. Some of these equatorial grains are charged, and some may be effectively neutral, and the balance of forces on them is not the same as on the magnetically captured grains at the mid-latitudes. They reach the planet by a different route, in a different place, governed by a different mix of forces. Why does this matter so much? Because it means that when people quote a single number for how fast the rings are losing mass, they are often quietly adding together two different processes, measured by different instruments, that may not behave the same way over time or respond to the same triggers. The clean, narrow definition of ring rain magnetic field lines, mid-latitudes, describes only part of the total mass loss. The big, dramatic equatorial downpour that Cassini tasted is not ring rain in the original strict sense at all. It is a separate, possibly more variable, possibly more episodic delivery of material. Lumping them together into one tidy figure is exactly the kind of false precision that turns a rich, uncertain reality into a misleading headline. Two doors, not one. Both real, both feeding the planet, but not the same door. There is a deeper physical idea lurking underneath both pathways, and it has a name worth introducing: the Roche limit. The Roche limit is the distance from a planet inside which the planet's tidal forces, the difference in gravitational pull across an object, are strong enough to overcome the gentle self-gravity that would otherwise let particles clump together into a moon. Inside that limit, material cannot easily gather itself into a single body. It is held apart, spread into a ring. Saturn's main rings sit largely within this zone, which is part of why they are rings at all rather than moons. But the same neighborhood that prevents ring material from assembling into a moon is also a hostile, dynamic place where orbits can be perturbed, grains can be charged and stripped away, and material that drifts inward toward the planet has no mechanism to save itself by becoming something larger and more stable. The Roche limit helps explain why the rings exist as a flat sheet of countless separate particles, and a flat sheet of countless separate particles is exactly the kind of structure that can be picked apart grain by grain and fed to the planet. The very geometry that makes the rings beautiful is the geometry that makes them vulnerable. Before we widen the lens to the rest of the system, there is a second cast of characters that has to enter the story, because the rings are not shaped by Saturn alone. They are sculpted, herded, and stirred by moons, small ones, embedded right in the ring system or orbiting at its edges, doing work all out of proportion to their size. They are called shepherd moons, and the name is exact. Just as a sheepdog keeps a flock in line by darting along its edges, these little moons use their gravity to corral ring particles, holding sharp boundaries that would otherwise blur and spread. Consider the gaps. Saturn's rings are not a single smooth sheet. They are cut by dark divisions, and several of those divisions are kept open by moons orbiting within them. A tiny moon named Pan circles inside the Encke gap, a clear lane near the outer edge of the main rings, and its gravity is what sweeps that lane clear, flinging stray particles aside and maintaining the empty channel. A still smaller moon, Daphnis, orbits within the narrow Keeler gap, and as it travels it raises waves in the ring, edges on either side, vertical ripples of ring material lifted into delicate, scalloped crests by the moon's passing pull, casting their own shadows when the lighting is right. These are not metaphors. Cassini photographed them. A moon the size of a small town, raising waves in a sheet of ice thousands of kilometers across. Then there is the F ring, a thin, twisted, knotted thread of material orbiting just outside the main rings, and it is held together by two moons, working as a pair Prometheus on the inside, Pandora on the outside, one orbiting slightly faster and one slightly slower, bracketing the ring between them. Their combined gravitational tugging confines the F-ring into its strange braided shape, constantly disturbing it, drawing out streamers and channels in the ring material. This is the same fundamental physics we have been describing all along. Gravity acting on countless small particles, but here it does something different from feeding the planet. It organizes, it carves structure into the rings, builds and maintains their edges, and stirs their material in ways that connect directly to the churning we will come to shortly. The moons keep the rings sharp, and in keeping them sharp they keep them moving, kicking particles onto new paths, some of which will eventually drift inward toward the planet's reach. The point is that the rings are not a passive sheet waiting to be drained. They are a worked surface, continuously sculpted from the outside by moons even as they are continuously consumed from the inside by the planet. The same gravity that builds the ring's structure is one step in the long chain that eventually delivers its material down into Saturn. Now let us widen the lens, because Saturn does not only pull material down, material is also being added to the system, and from a surprising direction which complicates the simple picture of a planet that merely consumes. Among the dark bands tied to the magnetic field, the O'Donoghue-led work identified one that sat at a higher latitude than the others, in the southern hemisphere. When the team traced the magnetic field line that produced it, the line did not lead back to the main rings. It led out to Enceladus, a small, geologically active moon orbiting well beyond the main ring system. Enceladus is famous for one spectacular trick. It sprays geysers of water ice into space from cracks near its south pole, fed by an ocean of liquid water hidden beneath its frozen crust. Those geysers, first seen by Cassini's instruments in 2005, supply a broad, tenuous ring of their own, the faint E-ring, and they also, it turns out, feed water down onto Saturn along the magnetic field lines that thread the moon's orbit. The same machinery that drains the main rings into the planet also pipes some of Enceladus's exhaled ocean down into Saturn's atmosphere. The planet is being watered from two reservoirs at once, the main rings up close, and a distant living moon far out in the system. This is where the phrase "one interacting system" stops being a slogan and becomes a literal description. Picture the full circuit. The rings orbit the planet. Grains within them are charged by sunlight and plasma. Saturn's magnetic field, anchored deep inside the planet and aligned almost perfectly with its spin, reaches up through the ring plane and grips those charged grains. Some it roots down to the mid-latitudes. Meanwhile, gravity and orbital decay drop other material onto the equator. Out beyond the main rings, Enceladus pumps fresh water into the same magnetic plumbing. And the arriving material does not just vanish on impact, it rewrites the chemistry of the atmosphere it falls into, quenching the ionosphere, clearing the haze, altering the carbon content of Saturn's upper layers. Planet, rings, moon, magnetic field, and atmosphere are not separate things that happen to be near each other. They are wired together into a single, continuously operating mechanism, exchanging mass and energy in a loop. The ring is part of the planet's body, and the planet is steadily digesting it. Cassini found one more piece of this wiring that deserves mention, because it shows just how electrically alive the system is. Buried in the magnetic data was an unexpected discovery, an electric current flowing through Saturn's upper atmosphere, generated by the interaction between the magnetic field and the bands of wind that race around the planet at different speeds. Saturn's equatorial winds blow fastest, with slower bands to the north and south. When a loop of magnetic field has one foot planted in the fast equatorial wind and the other in slower air, the winds drag on the charged plasma differently at each end, skewing the field line and driving a current through the atmosphere. The strength of that current was estimated to be comparable to a substantial number of large terrestrial power plants combined, a real, planet-scale electrical circuit running between the atmosphere and the inner ring region. And as a side effect, that current dumps heat into the upper atmosphere, which may help explain a long-standing mystery about why Saturn's upper layers are hotter than sunlight alone can account for. The rings and the field are not just moving mass. They are moving charge and energy, heating the planet, lighting it up from within in ways no one fully predicted. There was also that newly identified radiation belt, a long-suspected but previously unconfirmed band of trapped energetic particles sitting in the gap between the upper atmosphere and the innermost ring, sealed off from Saturn's main magnetosphere by the bulk of the rings themselves. It is a relatively weak belt precisely because the rings get in the way, soaking up particles that would otherwise build it up, and it may be part of why the falling water arrives chemically sorted, stripped of some of its ice on the way down. Even the radiation environment near Saturn is shaped by the presence of the rings, and in turn helps shape what the rings deliver to the planet. Everything touches everything. Let us now gather the mechanism into a single clear statement, because this is the heart of the entire story, and it needs to land without ambiguity. Saturn pulls its rings into itself through more than one process. In the strict, original sense, ring rain is the magnetic mechanism. Tiny grains of ring ice are electrically charged by sunlight and plasma, and once charged, the smallest of them are seized by Saturn's powerful, near-perfectly aligned magnetic field and guided down its field lines into the mid-latitudes, where they quench the ionosphere and clear the haze and print dark bands across the planet. Alongside that, and partly distinct from it, a heavier and possibly more variable influx of fine material falls more directly onto the equator, dragged down by gravity and orbital decay through the gap between the rings and the cloud tops. And feeding into the same magnetic plumbing, the geysers of Enceladus add water from far outside the main rings. These are not competing theories about one process. They are different, simultaneous, confirmed pathways by which the same planet consumes the same ring system. The metaphor of Saturn eating its rings is vivid, but it stands for something concrete and measurable. A structure in orbit being charged, gripped, decayed, and routed down into the world it surrounds, through magnetism and gravity working in concert. And notice what we have carefully not said. We have not said the rings are simply being sucked down by gravity, because that is wrong. A neutral grain in a stable orbit feels no inexorable pull to the surface, and the real mechanism depends critically on charging and on the magnetic field, not on gravity alone. We have not said the rings are mysteriously dissolving, because nothing here is mysterious in the sense of unexplained. The pathways are specific and traceable, even where their rates are uncertain. The eating is not magic, and it is not vague. It is electromagnetism and orbital mechanics, caught in the act by instruments that flew through the falling material and read it grain by grain. But understanding the mechanism immediately sharpens the question we began with, and turns it into something more urgent and more quantitative. We now know how the rings fall by what forces, through which doors, onto which latitudes. We know the planet has efficient machinery for the job, an aligned magnetic field and a gap full of decaying grains and a distant moon feeding the circuit. We have a system visibly, continuously moving mass from the rings into the planet. So the obvious next question is the one everybody actually wants answered. If Saturn is eating its rings, and we now understand how, then how long can the meal possibly last? How much time do the rings have before the doors we have just described carry the last of them down into the planet? It is tempting to take the rates we have seen, the 10,000 kilograms per second, the tens of thousands at the high end, the headline figures, and simply divide the mass of the rings by the rate to get a countdown. That arithmetic is easy. It is also a trap, because the mechanisms we have just laid out do not run at a single steady rate. They may surge and ease, they may be partly refilled, and the two main doors may not even behave the same way over time. Turning a measurement made over a few weeks into a precise expiration date for a structure older than the human species is exactly the kind of false confidence that good science refuses. So the next question is not just how long the rings have left. It is harder and more honest than that. How do we reason about the lifetime of a structure when the loss rate is uncertain, the refilling is real but unmeasured, and the very definition of how much is falling depends on which door we count? That is the problem we turn to now, and it is where the simple, satisfying story of a vanishing crown runs straight into the limits of what we are actually allowed to claim. There is a number that has travelled around the world. You have probably seen it, in a headline or a caption or a half-remembered fact. Saturn's rings will be gone in 100 million years. Sometimes it is 300 million. Sometimes it comes with an air of grim certainty, as if a cosmic clock were ticking down to a fixed date already circled on the universe's calendar. That number is not made up. It comes from real measurements and real scientists. But it is also one of the most misunderstood figures in modern planetary science. And the work ahead of us is to take it apart carefully, to honor what is solid in it, expose what is soft in it, and replace a false countdown with something more truthful and, in its own way, more interesting. Let us start with where the famous number actually comes from, because it has a clear and respectable origin. The estimate most people have heard traces largely to the work led by James O'Donoghue, the same scientist whose team mapped the infrared glow quenching in Saturn's atmosphere. The reasoning is straightforward in outline. If you can measure how fast water is draining out of the rings, and you know roughly how much ring there is to drain, you can divide one by the other and get a timescale. O'Donoghue offered a memorably concrete way to picture the rate. The ring rain, he said, drains an amount of water products that could fill an Olympic-sized swimming pool from the rings in about half an hour. From that mid-latitude ring rain alone, the arithmetic suggested the entire ring system would be gone in roughly 300 million years. And then, crucially, he added the other door. Fold in the much heavier flow of ring material that Cassini detected falling into Saturn's equator, and the timescale shortens dramatically to something less than 100 million years. He called it the worst-case scenario, and the phrase was apt. It is the fastest plausible drain, the version where the rings vanish soonest. 100 million years sounds like an eternity by human standards, and it is. But set it against Saturn's own age over 4 billion years and it becomes startlingly brief. If the rings are draining on a 100 million year timescale, then they are a fleeting feature on a very old planet, present for something like 2% of Saturn's existence. That contrast is the genuine, defensible core of the result, and it is worth holding on to. By the measured loss rates, the rings look young relative to the planet, and they look temporary. That much survives scrutiny. Now comes the harder, more honest part, the part the headlines almost always drop. Because the moment you try to turn "the rings look temporary" into "the rings will be gone in exactly 100 million years," you start making assumptions that the data does not support, and the false precision creeps in. Consider first what we have already established about the loss rate itself. It is not one number. 3 different Cassini teams came back with estimates of infalling material that disagreed by factors of thousands, from a few kilograms per second at the low end to tens of thousands of kilograms per second at the high end. They were measuring different materials at different latitudes with different instruments, catching different doors of the same system. The famous worst-case lifetime leans on the high end of that range, the heavy equatorial downpour. But if the true long-term average is closer to the low end, or somewhere in the wide middle, the lifetime stretches out correspondingly, potentially by a large factor. A countdown is only as precise as the rate you feed into it, and the rate we have is a smear across several orders of magnitude, not a clean figure. Consider next the problem of time. Cassini sampled the falling material over a window of weeks during its final orbits. The ground-based glow measurements span a longer baseline, but still a thin sliver of history. We are, in effect, trying to estimate how long a reservoir will last by watching the drain for a few moments, and assuming the flow we see is the flow that has always been and always will be, but the data themselves warn against that assumption. Recall that Cassini measured the rainfall changing from one orbit to the next, just days apart. The downpour is not obviously steady. It may surge and ease, and there is a specific, plausible reason it might have been unusually heavy exactly when we were watching. A recent collision. If a comet or a chunk of icy debris had struck the rings in the relatively recent past, recent in geological terms, it could have loaded the system with extra material, temporarily cranking up the infall rate well above its long-run average. In that case, the high numbers are real but transient, a storm we happen to fly through, not the climate. Scientists raised exactly this possibility, noting that the largest infall estimates simply cannot have been the steady state for long, because there is not enough mass in the rings to sustain that level of rain for the eons. The rings have plausibly existed. The rate that gives the scariest countdown may be precisely the rate that cannot have been typical. Then there is the deepest complication, the one that breaks the simple subtraction entirely. The rings may be refilling even as they drain. Throughout this story, we have spoken as if mass only moves one way out of the rings, into the planet. But Cassini's chemistry told a more circular tale. The heavy influx into the equator was being drawn largely from the innermost ring, the faint D ring. Yet the D ring is too thin to supply that torrent for long on its own. So where does its material come from? The answer the data pointed to is that the D ring is being continuously replenished from the ring just outside it, the more substantial C ring, which hands material inward. The thing we were watching pour into Saturn was, at least in part, being topped up from a deeper reservoir even as it emptied. As one scientist put it, ring rain is more like a ring downpour, but another framed the real lesson differently. The story is not about a fixed object quietly evaporating. It is about churn. The rings can be long-lived precisely because they are constantly moving and turning over, shuffling material inward and around, losing some to the planet while redistributing the rest. This churning has a formal name in the research literature: ballistic transport. The idea is that the rings are under constant gentle bombardment by micrometeoroids, tiny grains of debris drifting through the solar system. Each impact kicks up ejecta, sprays of material that fly off and land elsewhere in the rings, carrying mass and momentum from one place to another. Over long timescales, this bombardment and the transport of its ejecta reshapes the rings, moves material between them, and feeds the inner rings from the outer ones. Detailed models, notably the work of Paul Estrada, Richard Durazan, and colleagues, have shown that these processes can account for the observed loss rates with reasonable assumptions, and that an evolving ring subjected to this bombardment can develop structures resembling what we actually see, including a thin, low-density inner region much like the C ring forming from an initially more massive band. The point is not that the loss is illusory. The point is that loss and resupply are happening together, and the net lifetime depends on the balance between them, a balance we have not measured directly and cannot yet pin down. So when you put these three complications side by side, a loss rate uncertain across orders of magnitude, a measurement window too short to know the long-term average, an active refilling that partly offsets the drain, the clean countdown dissolves. It does not dissolve into we know nothing. It dissolves into something more careful. The rings are losing mass. The loss is real and confirmed. Losing mass, and by the measured rates they appear to be a temporary thing, set on an ancient world, but no single number should be treated as a precise expiration date. 100 million years is a useful order of magnitude statement about how short-lived the rings seem to be. It is not a date. Anyone who tells you the rings will vanish on a particular schedule has mistaken the worst-case end of a noisy, partial measurement for a fact. This is the right moment to draw a distinction that runs underneath the entire subject and is constantly, quietly confused even in careful coverage. The age of the rings and the lifetime of the rings are two different questions. Age asks, how long have the rings already existed? When did they form? Are they ancient, dating back to the birth of Saturn over 4 billion years ago? Or are they young, formed in the relatively recent past? This is a question about the past, answered by clues like how polluted the rings are, how much mass they contain, and how their composition has evolved. Lifetime asks, how much longer will the rings last? Given the rate they are losing material, when will they be gone? This is a question about the future, answered by loss rates and refilling, and the balance between them. These two questions are related. A structure that drains quickly is unlikely to have lasted forever, so a short lifetime hints at a young age, but they are not the same, and the evidence for each is different. You can have strong reasons to think the rings are young without having a reliable date for when they will disappear, and vice versa. Collapsing the two together is how you get the misleading impression that Cassini proved, both when the rings formed and when they will vanish, on a tidy schedule. It did neither with that kind of precision. I know, it gave us powerful constraints on both questions, with real uncertainty bars on each. Let us linger on the lifetime side a moment longer, because there is a subtlety that the churning picture introduces, and that almost never makes it into popular accounts. If the rings are a turning over system, losing material to the planet while being fed from within and reshaped by bombardment, then when will the rings be gone may not even have a single clean answer. Different rings may have very different fates. The faint inner D-ring might be drained and refilled on short cycles, a fast flickering structure. The massive B-ring, holding most of the system's mass, might persist far longer, slowly thinning. The artist's impressions that accompany the famous lifetime estimate actually capture this. They show the innermost rings disappearing first, raining onto the planet, followed only very slowly by the outer rings. The ring system does not switch off all at once like a light. It would fade unevenly, inside out, over a long and staggered decline. A single countdown number flattens that whole textured process into one misleading instant. There is also the question of what gone even means. Even the models that show the rings losing mass and developing a thin, C-ring-like structure suggest the system may approach a kind of long, drawn-out asymptotic state rather than abruptly vanishing, thinning towards something faint and sparse over enormous spans of time, with the bombardment and transport machinery still shuffling what remains. The end of the rings, if it comes, may be less a death than a long dimming, the structure growing fainter and more tenuous until it is no longer the glorious thing we see today, without there being a precise moment when the last grain falls. Now, having spent all this effort dismantling the false countdown, I want to be careful not to overcorrect into the opposite error. The uncertainty does not erase the central finding. Let us be clear about what remains solid after all the caveats. It remains solid that ring material is falling into Saturn directly measured by multiple instruments through multiple pathways. It remains solid that this represents genuine mass loss from the rings to the planet. It remains solid that the measured loss rates, even at their gentler estimates, are fast enough that the rings look temporary against the 4 billion year backdrop of Saturn's age. And it remains solid that the rings are not a static, eternal ornament but an active, evolving, churning structure with a finite past and a finite future. None of the uncertainty about the exact lifetime touches any of that. The debate is about the rate and the schedule, not about the direction. Saturn is losing its rings. We just cannot, in honesty, tell you the day they will be gone, and we should be suspicious of anyone who claims to. This careful posture, confident about the direction, humble about the timing, is exactly what good planetary science looks like when it is working properly. It would be easy to sell certainty. The certainty would get more clicks. But the real situation is richer than the certainty, because the uncertainty is itself telling us something. The fact that the loss rates vary so much, that the system seems to refill itself, that the measurement may have caught a temporary surge, these are not failures of the science. They are clues about how dynamic and alive the ring system really is. A structure that drained at one steady, boring rate would be easy to date and dull to think about. A structure that surges, churns, refills and varies is harder to pin down precisely because it is doing more. The messiness of the countdown is the fingerprint of a living system. There is a hard, practical reason the uncertainty is so stubborn, and it is worth being honest about, because it explains why we cannot simply go and settle the question. The instrument that gathered nearly all of this Cassini is gone. It burned up in Saturn's atmosphere in September of 2017, deliberately destroyed to protect the moons. There is, right now, no spacecraft orbiting Saturn. There has not been one since. Everything we have been weighing, the infall rates, the chemistry, the equatorial haze, the ring mass, comes from a single mission that ended years ago, much of it from a final burst of weeks. We are, in effect, trying to read the long-term behavior of a system from one fading snapshot, and the snapshot is all we are going to get for a long time. This matters enormously for the timing question, because the one thing that could actually pin down the ring's lifetime is precisely the thing we lack: sustained measurement over time. Recall the problem of the seasons, that the ring range should rise and fall as Saturn swings through its long 29.5-year orbit, exposing the rings to different angles of sunlight. To average that out honestly, to know whether the rates Cassini caught were typical or a seasonal peak, you would want to watch the infall steadily across a substantial fraction of a Saturnian year. Cassini watched for weeks. No campaign of a few weeks, however brilliant, can characterize a rhythm that takes decades to complete. We measured one beat of a very slow drum and are trying to infer the whole song. The ground-based telescopes and the Hubble Space Telescope help. They can track the infrared glow and watch features like the spokes come and go across the seasons, extending the baseline in a way Cassini alone never could. But they are working at the very limit of what is possible from a billion-some kilometers away, catching only the broadest strokes, unable to fly through the rain and taste it the way Cassini did. What would truly resolve the question is another orbiter, a mission that returns to Saturn, takes up a long watch, and measures the infall again and again over years, comparing its numbers directly against Cassini's to see whether the rates have held steady, surged, or eased. Only then could we replace a single snapshot with a trend, and a trend is what a real lifetime estimate requires. Until such a mission flies, the honest answer to "how long do the rings have" is not a number, but a shrug wrapped around a confident direction. They are leaving, we can prove it, and we will not know the schedule until we go back and watch for longer than we have ever watched before. The uncertainty is not a gap in the science, it is a gap in our presence at Saturn, and that reframing matters for how we should feel looking up at Saturn. The rings are not a doomed object counting down to a scheduled execution. They are a process, an ongoing exchange of mass between a planet and the debris around it, a balance tipped slightly toward loss, playing out over timescales so vast that across the entire span of human civilization, the rings have not visibly changed at all. Every astronomer, from Galileo onward, has seen essentially the same rings we see, because tens of thousands of years are nothing to this system. We perceive permanence, not because the rings are permanent, but because our lives, and even our species' entire history, are far too short to catch the motion. The rings are falling in slow motion, so slow that to us it looks like stillness. Which brings us, finally, to the question that all of this has been circling, the question that the lifetime debate cannot answer on its own, and that opens directly onto the last and deepest turn of our story. If the rings are losing mass on a timescale that, however uncertain, appears to be far shorter than the age of the solar system, if even the gentlest honest reading suggests they are temporary rather than eternal, then a profound implication follows, almost unavoidably. A structure that cannot last for billions of years and that we nonetheless see in full glory today probably did not last for billions of years. It probably has not been there since Saturn was born. The very brevity of the rings' future casts a long shadow backward over their past. If they are dying young, they were likely born young, and that turns the entire investigation around. We have spent this whole time watching the rings fall, understanding how they fall, and reckoning with how long they have left. But the loss itself, properly understood, is a clue to an even older mystery, the one the scientists kept circling back to even as they measured the rain. Knowing the rings are leaking, and roughly how fast, is a step towards solving the oldest puzzle of the whole Saturn system. Not when the rings will end, but where they came from in the first place. Why does Saturn, alone among the planets, wear such a magnificent crown? Were the rings always there, or did something happen relatively recently, in cosmic terms, to create them? And if they are young, what cataclysm gave birth to them while the dinosaurs may already have walked the Earth? That is the question waiting at the end of all this. The falling material has been pointing at it all along. We have watched the rings fall. We have taken apart the machine that pulls them down. We have learned to distrust the tidy countdown and to hold the loss as real, but the schedule as uncertain. And at the end of all that careful accounting, one implication kept surfacing, quiet but insistent, until it could no longer be set aside. If the rings are dying young, they were probably born young. The very fact that they are leaking carries a message about their origin, and that origin is the oldest and strangest question in the whole Saturn system. Not when the rings will end, but why they exist at all. Begin with how genuinely odd it is that Saturn has these rings. Every giant planet in our solar system has rings of a sort. Jupiter wears a faint, dusty band, easy to miss. Uranus has a set of thin, dark, narrow rings. Neptune has delicate, clumpy arcs. Rings, it turns out, are not unique to Saturn at all. They are a common feature of the outer worlds, a natural consequence of debris caught near a massive planet. But there is no contest, no comparison, between those whispers of rings and the structure Saturn carries. Saturn's rings are bright, broad, massive and spectacular in a way nothing else in the solar system approaches. They are the difference between a pencil line and a cathedral. So the puzzle is not really, why do planets have rings? It is sharper and more personal than that. Why does Saturn, and Saturn alone, wear something this dazzling? What happened here that did not happen at Jupiter, at Uranus, at Neptune? It is worth letting that contrast do real work, because the faint rings of the other giants are not a side note, they are a control group, and they sharpen the mystery rather than dilute it. Jupiter's ring is a thin veil of dark dust, so faint it was not even discovered until a spacecraft went looking for it, and it is continuously resupplied by dust, knocked off small inner moons by micrometeoroid impacts, a wispy, self-renewing haze, not a great structure of ice. The rings of Uranus are narrow, dark and rocky-looking, more like sooty threads than anything bright. Neptune's rings are fainter still, broken into clumpy arcs. What every one of these has in common is that it is dim and it is dark, dominated by dust and by non-icy carbon-rich material, the very stuff that long exposure to space leaves behind. And that is exactly the point. Dim, dark, dusty rings are what you would expect from ring systems that are either very old, thoroughly polluted by eons of bombardment, or perpetually rebuilt from the grime of nearby moons. Saturn's rings are the opposite of all of that. Bright, broad, and overwhelmingly clean ice. They do not look like the others because, by every line of evidence we have, they are not like the others. The other giants wear the faint, weathered rings that the slow processes of the solar system tend to produce. Saturn wears something that looks newly minted, a vast quantity of clean ice that the ordinary, gentle, ongoing processes around a planet do not produce on their own. The comparison forces the question into its sharpest form. The faint rings of Jupiter, Uranus, and Neptune can be explained by everyday wear and resupply. Saturn's cannot. Its rings demand a special cause, a discrete event, something that put a great deal of clean ice into orbit in the geologically recent past. Exactly the kind of catastrophe the rest of this story is about to examine. The other ringed planets are not a distraction from Saturn's story. They are the evidence that Saturn's story needs an extraordinary explanation. For most of the history of the question, the default assumption was that the rings were ancient. It felt natural to imagine that they had been there since Saturn formed, leftover material from the planet's birth over 4 billion years ago, a primordial disk that never gathered into moons, an eternal feature of an eternal planet. The trouble is that the evidence, gathered patiently and then decisively by Cassini, has been pushing hard in the opposite direction. The rings, by several independent lines of reasoning, appear to be young, not billions of years old, but something on the order of a few 100 million years or less. Young enough that, if true, they did not exist when most of Earth's history was already over. Young enough that whatever made them may have happened while complex life was already swimming and crawling on our own world. Let us walk through the case for youth, because it is one of the more elegant pieces of detective work in planetary science, and then we will give the counter-argument its full and fair hearing, because the honest state of this question is a live debate, not a settled verdict. The first clue is mass. During the grand finale, as Cassini threaded the gap between the planet and the rings, the spacecraft's path was bent ever so slightly by the gravity of the rings themselves. By measuring those tiny tugs with exquisite precision, scientists weighed the rings for the first time directly. The answer surprised them. The rings are light. Their total mass came out to roughly 4/10 the mass of Mimas, one of Saturn's small inner moons, a body only about 400 kilometers across. The entire glorious ring system, spanning a width you could lay several Earths across, weighs less than half of a modest little moon. And this matters for age because a low mass is a low buffer. A light ring has less material to hide its history in and less to lose before it is gone. The second clue, and the most powerful, is purity. Saturn's rings are overwhelmingly water ice. By most measurements between 95 and 99%, clean, bright ice. And here is why that is a clock. Space is dirty. The solar system is full of micrometeoroids, tiny dark grains of rocky and carbon-rich debris drifting between the planets, and they rain steadily onto everything, including the rings. Over time, this constant bombardment should darken and pollute pristine ice, mixing in non-icy material, dimming the brightness, staining the white. If the rings had been sitting out in this drizzle of cosmic soot for 4 billion years, they should by now be filthy grey, contaminated, heavily polluted. Instead, they are strikingly clean and bright. The reasoning then runs like this. Assume the rings started as pure ice. Measure how dirty they are now. Measure how fast the dirt arrives, and divide. The pollution they carry is consistent with only a few 100 million years of exposure, not billions. The rings look freshly made because, by this argument, they are freshly made. Cassini nailed down the crucial missing piece in that calculation, the rate at which the dirt actually arrives. Its cosmic dust analyzer made the final, definitive measurements of the micrometeoroid flux falling into the Saturn system. How much exogenic material, debris from outside, is raining onto the rings. That work, led by Sascha Kempf and colleagues, and published in 2023, combined with the measured pollution fraction and the measured ring mass, tightened the constraint, an exposure age of no more than a few 100 million years, on the order of 100 to 400 million, assuming the bombardment has been roughly steady over that span. 3 separate Cassini measurements, the mass, the pollution level, and the incoming flux of dirt all pointing the same way toward youth. Add to that the mass loss we have spent this whole story documenting, the rings visibly draining into the planet, and the picture sharpens further, a structure that is both losing mass and apparently not very old, ephemeral, coming and going. That is a strong, multi-pronged case. For several years it carried the field, and Saturn's rings are young, hardened from a provocative claim into something close to a consensus. But science is not supposed to stop at a satisfying answer, and in the last couple of years the youth hypothesis has met a serious and fascinating challenge, one that turns on the deepest assumption in the whole argument. Look again at the logic of the purity clock. It assumes that when micrometeoroids strike the icy ring particles, the non-icy material sticks that the dirt accretes, accumulating in the ice and darkening it over time. The exposure age is calculated on the premise that a high fraction of the impacting pollutant is retained. But what if it is not? What if the ice is better at staying clean than anyone assumed? This is precisely the question that recent work has pressed, and the results complicate everything. In 2024 and 2025, researchers ran detailed numerical simulations of what actually happens when a micrometeoroid slams into an icy ring particle at the brutal speeds typical of the Saturn system, tens of kilometers per second. The work of Ryuki Hyodo and colleagues, modeling impacts on ice at around 30 kilometers per second, found that the impactor and part of the target are almost entirely vaporized, and that the great majority of that vapor, more than 97% in their model, then escapes the ring system entirely, rather than settling back onto the ring particles as pollution. A parallel result published in Nature Geoscience argued, from simulations of hypervelocity impacts, that non-icy material may simply not be accreted as readily as the youth calculation assumes. If the pollutant largely vaporizes and flees instead of staining the ice, then the rings could stay bright and clean for far longer than the simple clock allows. They could look young while being old. Sit with what that does to the argument. The entire purity-based case for youth rests on the assumption that dirt accumulates efficiently. If dirt mostly bounces off and escapes, the rings could be brilliantly clean and ancient at the same time, and the few 100 million year exposure age becomes a serious underestimate. The strongest pillar of the young ring hypothesis turns out to rest on a number, the accretion efficiency, that we are still arguing about. I want to be scrupulously fair here, because this is exactly the kind of place where it would be easy to overstate one side. The pollution resistance results are not a knockout blow, and their own authors and reviewers have flagged their limits. The very low retention figures are upper bound estimates that assume the recondensed material keeps its darkening properties, which is not certain. The simulations make simplifying assumptions about the size of impactors relative to targets, about the porosity and strength of ring material that may not hold across the real, varied population of ring particles, and a very low pollution retention rate creates new problems of its own. It becomes harder to explain certain features of the rings, like the way the composition transitions between the C ring and the B ring, which the older, dirt accumulates picture handled more naturally. So the field has not swung from young to old. It has swung from young fairly confidently to young is still the leading interpretation, but the central clock is genuinely contested, and ancient rings are back on the table in a way they had not been for years. That is the honest state of the question as it stands, a leading hypothesis, seriously challenged, not overturned. And this is where I want to be careful with the kind of language this subject invites, because the distinction between confirmed fact, leading hypothesis, and open debate is the whole discipline of thinking clearly about Saturn. That ring material is falling into the planet confirmed, measured directly. That the rings are losing mass confirmed. That the rings appear young, relative to Saturn, a strong and leading hypothesis, well supported but now actively contested at its foundations. That the rings formed in one specific recent event, on one specific date, speculative, unresolved. Keeping those tiers separate is not pedantry. It is the difference between knowing what we know and pretending to know what we do not. So, set the age debate to one side for a moment, unresolved, and ask the other half of the origin question, the one that does not depend on settling exactly how old the rings are. Where did the material come from? Whatever their precise age, the rings are a vast quantity of remarkably pure ice arranged in a flat disk. How do you make that? There are competing scenarios, and they are genuinely competing. No single one has won. One family of ideas says the rings are the corpse of a moon. Imagine an icy moon, sometime in Saturn's past, wandering too close to the planet, close enough to cross inside the Roche limit, the boundary we met earlier, where the planet's tidal forces overwhelm a body's own feeble self-gravity and tear it apart. A moon shredded inside that limit would not fall to the planet as a lump. It would be strung out into a disk of debris, its ice flung into orbit as countless particles, and over time that debris would settle into a ring. A purely icy moon, or one whose rocky core was somehow disposed of, could plausibly yield the strikingly clean ice we see. Before we follow that idea to its most startling conclusion, it helps to notice that the rings are not the only thing in this system whose orbit is visibly changing. So are the moons, and one of them, it turns out, holds the key to the most elegant origin story we have. We have spent this entire film watching ring material spiral inward and fall into the planet, a slow rain of ice drawn down out of the sky. But out beyond the rings, the traffic runs the other way. The large moons are climbing, drifting outward, slowly spiraling away from Saturn over time. The rings fall in, the moons climb out, and both motions are the same underlying story, a system in restless orbital evolution, caught by our instruments in the act of changing. The mechanism that lifts the moons is tides. A large moon raises a bulge in the planet it orbits, the way our own moon raises the ocean tides on Earth. That bulge does not sit perfectly beneath the moon. It is dragged slightly ahead by the planet's spin, and the gravitational tug of that displaced bulge slowly feeds energy into the moon's orbit, nudging it outward, year after year. Earth does this to our moon. It drifts away from us at about 3.8 centimeters per year, roughly the rate your fingernails grow. The same physics operates at Saturn, but here it produced one of the genuine surprises of the post-Cassini era. Two independent teams, using two different techniques on a decade of Cassini data, one mapping Titan's position against background stars, the other reading Titan's gravitational pull on the spacecraft itself, measured how fast Saturn's giant moon Titan is moving away. The expectation, from standard tidal theory, was a crawl. At Titan's great distance, perhaps 1/10 of a centimeter per year, almost too slow to detect. What they found instead was 11 centimeters per year, more than 100 times faster than the old theory predicted. That number matters enormously for the story we are about to tell, because a moon migrating that fast is a moon capable of reaching across the system and rearranging it. If Titan is sweeping outward more than 100 times quicker than anyone thought, then, over the relatively recent past, it can have swept through gravitational relationships with other moons, drifting until its orbital rhythm lined up with theirs, tugging on them in sustained, building pulses, the way a push delivered at just the right moment in each swing drives a child on a swing higher and higher. A fast migrating Titan is a Titan that can destabilize its neighbors, and that is precisely the lever the most elegant origin hypothesis reaches for. The rings falling inward and Titan climbing outward are not two unrelated facts about Saturn. They may be two ends of the same chain of events, the moon's restless outward march, reaching back, in the end, to write the rings into the sky. This idea found its most striking and specific form in 2022, in a hypothesis that is genuinely one of the most elegant in recent planetary science. And it begins, of all places, with a problem that seems to have nothing to do with the rings. Why Saturn is tilted. Saturn leans. Its spin axis is tipped by about 27 degrees relative to the plane in which it orbits the Sun. And I want to be careful here, because this is a different tilt from the one we met earlier. Earlier, we talked about Saturn's magnetic axis being almost perfectly aligned with its spin axis. That is the field versus the spin. This is something else entirely. The spin axis itself, leaning over relative to Saturn's orbit. The same kind of tilt that gives a planet seasons. And that lean is a puzzle, because a giant planet built up from a swirling disk of gas should have formed spinning nearly upright, not tipped over by 27 degrees. For years, the leading explanation tied Saturn's tilt to distant Neptune. Saturn's axis wobbles, or precesses, like a spinning top, and it happens to precess at very nearly the same rate that Neptune's whole orbit wobbles. That near match looked too close to be coincidence. It looked like a resonance, a gravitational lockstep between two planets a billion miles apart. But when a team led by Jack Wisdom at MIT used Cassini's final precise measurements of Saturn's gravity to pin down exactly how mass is distributed inside the planet, they found something that broke the neat story. Saturn, as measured, sits just slightly outside that resonance with Neptune today. The lockstep is almost there, but not quite. Something, it seemed, had nudged Saturn out of the resonance in the relatively recent past, and the team's proposed culprit is breathtaking. A lost moon. They named it Chrysalis. The proposal is that Saturn once had an additional major moon, roughly the size of its present-day moon Iapetus, which orbited quietly for billions of years while the resonance with Neptune held and Saturn's tilt was maintained. Then, sometime between about 200 and 100 million years ago, the same slow outward migration of Titan we just traced reached across the system and destabilized Chrysalis's orbit, tipping a quiet neighbor into ruin. The lost moon began a chaotic dance, suffered close encounters with the other moons, and finally swung so close to Saturn that it grazed the planet and was torn apart inside the Roche limit. The loss of that moon changed how Saturn's mass and moons were balanced, releasing the planet from its resonance with Neptune and leaving the tilt we measure today. And the debris from the shredded moon, the fraction that was not swallowed by the planet, settled into orbit and became the rings. Because Iapetus is made almost entirely of water ice, a moon of similar makeup is exactly the kind of body that could yield rings of nearly pure ice. The beauty of the idea is that it explains two utterly different mysteries with a single event. The young age of the rings and the unexplained tilt of the planet, long treated as separate problems, become two consequences of one catastrophe, roughly 100-some million years ago, recent enough that, as the researchers themselves noted, dinosaurs walking the Earth might have looked up at a ringless Saturn, and then, in some later age, at a Saturn newly crowned. The name captures it perfectly. A chrysalis, dormant for billions of years, that suddenly transformed into something glorious. But, and this is essential, the chrysalis hypothesis is exactly that, a hypothesis and a frankly speculative one. Its own authors are careful about it. In their simulations, the specific chain of events that destroys Chrysalis and makes the rings did not happen most of the time. Only a modest fraction of the runs produced the desired outcome. Other planetary scientists have called it plausible, but not necessarily likely a good story that will have to be tested by others, perhaps confirmed or ruled out by future, more precise measurements of how Saturn, its moons, and Neptune actually move. It is a candidate, not a verdict. It belongs in the tier of ideas we entertain seriously, while withholding final judgment, and it is not the only candidate. A second family of ideas points outward, to the wandering bodies that cross the outer solar system, a large comet or a passing icy interloper, captured and disrupted by Saturn's gravity, its material spread into a ring. A third set of recent models takes a more violent route still. Detailed simulations published in 2023, led by Jacob Kegeris and colleagues, modelled actual giant impacts between large icy bodies in the Saturn system, full-blown collisions powerful enough to scatter enormous quantities of ice into orbit. These simulations explored whether a relatively recent crash between two big icy moons could have produced the rings, and potentially some of Saturn's mid-sized moons as well, in a single connected event, flinging out clean ice while sending rockier material elsewhere. Each scenario, the disrupted moon, the captured comet, the giant impact has its strengths, and each has unanswered objections. What they share is a common shape. Something was destroyed to make the rings. The crown is built from a catastrophe. That shared shape is worth dwelling on, because it reframes the beauty of Saturn in a way that is almost unbearable to hold in the mind at once. The most serene, most perfect-looking object in the solar system, the thing we put on the covers of children's books to mean space, the calm, jeweled planet, may be the visible wreckage of a violent death. A moon torn apart, a comet shattered, an icy body destroyed and smeared into a glittering disk. The serenity is the afterglow of a catastrophe, and on the clock of the solar system, a startlingly recent one, the debris still so bright and so undimmed that the violence which scattered it might well have unfolded within the last long stretch of Earth's own, very ancient, history of life. This is the place in our story where it is finally right to step back from the instruments and the numbers and ask what all of it means, because we have earned the reflection by doing the work first. Here is the thing that the whole investigation finally delivers. The rings are not an ornament. We have called them a crown, a halo, a set of bangles, jewellery, and every one of those words quietly carries the assumption that they are decoration, something added to the planet, separate from it, permanent and inert. The science dismantles that assumption completely. The rings are a structure with a biography. They had a beginning, a moon's death, or a comet's, or a collision, sometime in a past we are still trying to date. They have a present, an active churning system, charged by sunlight, gripped by a magnetic field, draining into the planet through more than one door, refilling itself even as it leaks, exchanging mass and charge and heat with the world it surrounds. And they will have an end, a long, uneven fading. Inner rings first, the great mass thinning slowly behind them, until whatever remains is no longer the glory we see now. Birth, life and death, on a timescale so vast it masquerades as permanence. The rings are not a thing Saturn has, they are a thing Saturn is doing, and that recasts our own relationship to them in a way that is genuinely humbling. Across the entire span of recorded human history, the rings have not visibly changed. Galileo, squinting through his crude telescope in 1610, saw something he could not quite resolve, strange handles or ears on either side of the planet, a puzzle he never fully solved. Every astronomer since has seen essentially the rings we see tonight, because tens of thousands of years are nothing to this system. The motion we have spent this whole story documenting the falling, the draining, the slow decline is real, but it is so slow, by the measure of a human life, that it presents to us as perfect stillness. We are like someone who glances at a glacier and sees an unmoving wall of ice, never suspecting it is a river. The permanence of the rings is an illusion authored entirely by the shortness of our lives, which means something quietly astonishing about the moment we occupy. If the rings are indeed young and even with the age debate unresolved, that remains the leading reading, then they did not exist for most of Saturn's history, and by the loss rates we have measured, they will not exist for most of its future either. They're a feature of the middle, a passing phase, and we are here to see them. Out of the 4 billion year life of this planet, across an epoch in which Saturn may have been bare for ages before and may be bare again for ages after, we happen to be alive during the relatively brief window when it wears its rings in full splendour. That is not a small thing. It is, if you let it land, a staggering piece of luck. The most beautiful object in the solar system is not a fixed fact of the universe. It is a temporary event, and our species arrived in time to witness it. We should resist the cheap version of this thought, the sensational one, the see Saturn's rings before they're gone, urgency, as if there were a deadline and a ticket to buy. There is no deadline we can name. The rings will outlast not just us, but very likely our species, our descendants, and any civilization we can presently imagine. The window is brief on a cosmic scale and effectively eternal on a human one. The wonder is not that we must hurry. The wonder is that we exist at all during the act, that the timing of a curious, upward-looking species and the timing of a planet's crowned phase happen to overlap, that we evolved eyes and built instruments precisely during the interval when there was something this magnificent overhead to point, the mat. That overlap is the quiet miracle the whole investigation arrives at. The rings did not wait for us, and they will not wait for anyone after us. They are doing what they have always done, being born from violence, living as a restless system of ice and charge and magnetism, and falling, grain by grain, into the planet below. Saturn is, in the only sense that matters scientifically, slowly consuming its own crown, not out of any will or hunger, but through the patient operation of gravity and electromagnetism on a structure too finely divided to defend itself. And we, on our small wet world a billion kilometers away, were granted the brief and improbable privilege of looking up, understanding what we saw, and realizing that the most permanent seeming thing in the sky was never permanent at all. It only looked that way because we did not stay long enough to see it move.